All right, thank you very much for the introduction. Let me just try to go full screen here. Can everyone see my screen and hear me?
Yep, very good.
Okay, so first of all, welcome to the open house, and thanks for the invitation to speak here. So today I'm going to talk about some mathematical questions that concerns machine learning that could be of interest to prospective graduate students who want to work in areas of mathematics and its intersection with data science. So if you think about machine learning, right, we think of something that's very recent, or at least that's what it appears to be. So we have a lot of very interesting applications of machine learning, say in self-driving cars, machine translation, how you use Google Translate easily now, and also the hallmark achievement of machine learning in beating one of the top human Go players by this program called AlphaGo, right? So all these are very recent advancements, and from the way that it's covered, it seems to be very recent developments, okay? But on the other hand, if you think about mathematics, you tend to think it's something that's really old, right? This elements by Euclid, which is like, many long time ago. So the naive thing to think is that, okay, machine learning is something very new, but mathematics is something that's very old. So what is really the connection between the two? Now, what I want to try to convince you in this talk is that this is not, true in general, okay? And it sometimes is the opposite. Okay, so let's take a little trip back to, very ancient times. So ancient astronomers have observed that some of the stars in the sky, okay, they don't stay stationary, and they move around, okay, as you observe it every day. And we call this retrograde motion, and you'll see later what I mean by that. And the ancient Greeks named them planetae, okay, which we now know, adopt the term planets. Okay, this actually means wanderers. And okay, so what does that look like? Let's look at how the things appear to be on Earth. So now this video shows the perspective of observer on Earth as we observe Mars, right, which is moving here, okay, against a backdrop of stars that's not really moving. And now you see that the Mars appears to turn around, okay, which is very strange, right? And then it goes the opposite way, and after a while, it stops again, and it turns back around. So to the ancient astronomers, this is very strange behavior, right? Of course, now we know why this is the case. So let's watch it again. You have this Earth, and the Mars moves to the left, okay, and then it slows down and begins to turn around. Okay, and then you will move again, stops later on, and we call this retrograde motion. And this is very curious to the ancient astronomers, but today we know why this is the case, right? Because this is actually, the reason behind this is that we are actually also moving around the sun, all right? From the perspective of the Earth, when our orbit overtakes the Mars orbit, because we have a higher angular velocity here, then the Mars appears to be moving away from us, okay, and so on and so forth. So using this heliocentric model, where we know that the sun is in the middle of the solar system, then this becomes a very obvious thing. However, to the ancient astronomers, this is not so obvious. So for some reason, we tend to believe that the Earth is actually in the center. Okay, so then very troubling, a very curious question to the ancient astronomers is that if you really look from the perspective of the Earth, a lot of the celestial bodies, so I just take Mars as an example, it moves around in quite an erratic motion, right, retrograde motion. So how do we make sense of this seemingly irregular motion of Mars? Okay, so this is kind of a mathematical question or astronomical a question in astronomy that was posed by very early scientists. And a very well-known mathematician, one of the most influential mathematicians, Ptolemy, especially for in the area of plane geometry, he studied this problem. So he thought, how can I construct a model to understand why the orbits move the way they do? And his idea is a very interesting one. His idea is to construct irregular orbits by composing some regular ones, like circles. Okay, so how does that work? Suppose we are given an orbit that's perfectly circular. Then circles are nice geometrical objects. So Ptolemy thought, okay, I can just put a circle on this orbit, and then I just model this orbit by two numbers. The first number is the radius of the circle, okay, and the second number is the angular velocity, or rather how fast this circle, this object turns around the circle. All right, so this is kind of simple. I just need to specify two numbers. And then when you observe Mars, it actually doesn't move in a circle, right? So with respect to Earth, right, it moves in a very erratic orbit, as we shown just now. So how does Ptolemy solve this issue? He says that, well, to produce irregular orbits, or at least not circular orbits, what I can do is the following. I take another circle. So I imagine that I have a circle here, and it has a, this hidden points moving along the circle, and Mars is actually moving on another circle that's centered on the first circle's point. Okay, so you can see that this orbit, the orbit that this setup traces out is a much more complex one. And of course, you can go even more, model even more complex orbits in the following way. So maybe all of you would have guessed how that works. We just have more and more circles, right? So for this very irregular orbit, we'll have three circles. They are arranged in exactly the same manner. So for example, to specify the second orbit, you need four numbers, right? The radius of the first circle and how fast it turns, the angular velocity, and the radius of the second circle and how fast it turns. Okay, and this one you will need six numbers, and so on and so forth. Now, the interesting question is, from a mathematical point of view, is this a good model or not? Okay. In the end, I think Ptolemy built a very comprehensive model of the planets in the solar system, the things you can observe, which is at that time, I think 4 or 5. And he managed to build a very accurate model of the motion of these planets by using something like a few hundred circles. Okay, so maybe naively you might think that this is a terrible model, because today we know that we can calculate the orbits of this to very high precision by just following one formula from Newton's laws. Okay, but let's hold that thought a moment and see, is this really a bad model? Okay, or is it a good model? Now to fast forward to modern machine learning. See, if you read the news, or if you have already done some machine learning work, this should not be very new to you. So modern machine learning, one very interesting area that we have been exploring is so-called neural networks. So what does neural networks do? Okay, again, this formula is not so crucial to pass, but what it does is it feeds some input into a network kind of architectures to compute output. Okay, so mathematically, the neural network will look something like this, which is a linear combination, okay, sum over aj, where aj is just some numbers, of some product of my weights. These are the things I can learn with my input. Okay, so this is some sort of formula that you can use to compute this neural network. Okay, again, the formula is not important. And what is the goal of the neural network is to learn some target function, right? So we think about the target relationship. Let's say, we have a perfect classifier that can classify, pictures of cats and dogs perfectly. Okay, so in that case, the Y will be the label cat or dog, and X will be the pictures of cats and dogs. Okay, and our goal of neural network is to train these weights, learn so that they are approximately equal. So we can use our neural networks to actually tell when a cat is a cat and the dog is a dog. Okay, of course, we have more serious applications of it. Now the question, a very interesting one, is this fundamentally different from Ptolemy's approach in modeling the orbits? Okay, so let's take a look at this question. Now, Ptolemy's goal from the outset is to fit some function, okay, on data. And this function is precisely the curve that's traced out by the orbit. So essentially, the goal of this tool, right? One is neural networks to learn, say, a classifier of cats and dogs, and Ptolemy's model to learn, how to predict the orbits. They're essentially the same problem. But I want to convince you that actually it's not just that they're essentially the same problem. They are also mathematically almost the same problem. Why is that the case? If you look at our original, the first kind of Ptolemy's model of one circle, okay, so this is, you just specify the radius and the angular velocity, how fast it turns. we can actually write it down mathematically as the following model. So we imagine that the Mars is moving, with some coordinate. Okay, so this, let's call it ZT, and it's a complex number. And we plot its real part on the x-axis and imaginary part on the y-axis, right? And then now you can actually write a formula, if you remember from say school, that this is just the usual exponential representation. So AI is the radius of this or the modulus of this complex number, and this is the period or the phase. Okay, so A1 and W1 will specify the radius and the angular velocity of this. Okay, so what happens when you have two circles? Obviously, you just add two of this together with different radii and different angular velocity, and so on and so forth. So if you have many circles, then you just have a formula which is just a linear combination of a bunch of exponential functions. And now, if you compare this to neural networks, you see that they are essentially the same thing, except that you choose a particular function, okay, for the so-called activation function. Okay, again, don't have to pay attention to the details, but what I wanted to say is that actually Ptolemy, in some sense, is using a neural network, okay, to fit the orbits. And in fact, this is a very special neural network. This, for those of you who have learned Fourier transform, you might have already seen, you might discover that this is exactly the Fourier transform of this orbit. So what Ptolemy did on the outside may look like a bad model, but mathematically it's a very deep result. It says that any curve, any smooth curve can be broken down in terms of Ptolemy's model. And you can always find this period and this radii. And this is due to Joseph Fourier, who, of course, studied the Fourier series of Fourier transform in an entirely different setting in its problem of heat conduction. Okay, but they're essentially the same problem. And that's a recurring theme in mathematics, is that when you really get down to the mathematical basis of a lot of different problems, you realize that they share a lot of similarities. Okay, so this is essentially the same problem mathematically. So why do we even study neural networks now? Let's say machine learning for neural networks now. I want to convince you that it's the same, but the mathematical questions might be a bit different. The first difference is that in Ptolemy's model, the input is just time, which is one-dimensional. Okay, but in current applications of neural networks, we're always, dealing with the very high-dimensional problem. So, for example, if my input is an image, and then this d here will be the number of pixels in that image, which is going to be huge. So how does this whole approximation idea, that can all be traced back to the roots of harmonic analysis, of Fourier analysis, how does this scale when your dimensions increase? Now that's a very interesting mathematical problem, and there's much is really unknown as of today. And the second thing is you have statistical issues of the fact that you do not have the liberty to observe, like as Ptolemy did, the orbits exhaustively. Because when you are in low dimensions, you can just observe the planets every day, and eventually you will have collected almost all the data that you need. However, in high dimensional problems, you have this issue of cursor dimensionality. So this is a little cartoon that illustrates this fact. So the shaded area is where you can collect data. Let's say you have some budget and you can collect some data. And you can see that in lower dimensions, okay, this is just some cats and dogs. In the lower dimensional space, if you draw some data, you are going to get a very good representation of cats and dogs. But as you increase the dimension, the data becomes more and more sparsely distributed in the set, right, in the entire space. So now it becomes much harder to actually get a representative sample. So the interaction of dimension and the statistical aspect of this, it really paints you quite a different mathematical picture. And there's a lot of other kind of interesting mathematical questions you can ask, and you really have to address for modern machine learning. So again, it's the same thing, but it's somewhat different. Okay, so let me just give you another example. Now, much of the modern progress, let's say for AlphaGo, the progress actually rely on deep learning. So deep learning is another form of neural networks that takes this original kind of shallow structure, so the one that I showed you, and make a deep one out of it. So they take many layers of neural networks stacked together. Okay, so this is what's new in deep learning. And mathematically, you can think of this as some sort of function composition. So you are composing many different functions together, and that gives you a new kind of complexity that arises. Okay, so this in deep learning, the complexity arises from this stacking of neural networks together. So now there's another question, the same question, right? Is this a new phenomena? So again, this is actually not a new phenomena, at least from certain mathematical viewpoints. And I want to again travel back in history and go to the 1700s during the development of calculus. So the again, the prominent mathematician Johann Bernoulli, he posed the problem to many of his contemporaries, including Isaac Newton. Okay, so he asked the problem: if I roll down a ball from point A to B, okay, and I can build a ramp, okay, what kind of shape of the ramp can I build such that the ball rolls down to the hill most quickly? And the problem is very simple to pose, but actually the solution is not so easy. And but then again, Isaac Newton did give the correct answer, and the answer is cycloids. So these are the curves traced out by a wheel when you turn the wheel. Okay, so if you don't know this, be sure to read up on why these are cycloids. It's very interesting. And this little question just led to the development of the field called the calculus of variations, which later developed into optimal control, which are essentially how do you perform calculus or differentiation and then minimization, optimization on curves, things of very large dimensions that are dependent on each other in time. And these are many of the mathematical giants that made significant contributions. Okay, so what has this got to do with machine learning? It turns out that the deep neural network architecture has a lot to do with this idea of optimizing over curves. And to give you an example, okay, so the deep neural network has many layers together that are composed together, and it's very difficult to analyze. It is highly nonlinear, whatever difficulties arises, you will be here. But this problem is not new in the sense that we have dealt with this problem, for example, in the analysis of solids and fluids. Okay, so how do we deal with this problem? We say that instead of peeking at the architecture or the structure of these atoms and molecules, we can zoom out and imagine them to be a continuum. Okay, once we imagine them to be a continuum, we can derive nicer equations that work in a macroscopic scale, and that will tell us a lot about the behavior of these solids and fluids. And the same idea can be used for neural networks. We can idealize them as a continuum, kind of a dynamical equation, so that we zoom out from the layers and consider just the evolution of these inputs as you feed across this network. Okay, so this becomes very much like now you need to optimize the dynamics, right? So this becomes very much like a particular problem of calculus of variations. Now you are optimizing over how you transform the features across a deep neural network, which is now you can think of as a dynamical system. Okay, so this is some very recent development that also traces its roots, to hundreds of years ago. But again, the recurring theme is the same but different. So now our goal is to analyze this, right? This deep neural network with which transforms, instead of this ball rolling from A to B, now it rolls kind of the input from low-level features like edges to high-level features like the features of the faces. Now, your goal is to control how this evolves so that you can, make the neural network do whatever you want, like say recognize a face. So what's different here is that the trajectories now are very random because you have many different faces, right? So it's not just one particular face. You can think of it as many different ramps that you have to build. And this then points to the fact that the stochastic or probabilistic and statistical aspects will be intertwined with the dynamical aspect and optimization aspect that we talked about before that has been studied for hundreds of years. So this is again a new question that can be posed for all mathematical problems. Okay, so overall, what does the mathematical theory of machine learning look like? I think it has to have certain very important components, like how do you develop approximation theory and harmonic analysis in high dimensions, okay? And how do you optimize things that are in high dimensions? And whether, can we determine the statistical aspects, of the learning theory in such settings? And what should you do? What is the point of developing this mathematics? Is so that we know how to build models, how to select models, and how to select algorithms in practice. And further, we want to provide some performance guarantees that we can impart to the practitioners so that we can know that certain model is efficient or is efficient or safe, for practical use. Okay, so in one sentence, is the development of mathematics for machine learning is to try to open some black box properties of this current machine learning, especially deep learning. Okay, so the punchline is that machine learning is not new. It's not a new problem, but and the mathematics that we need to develop is certainly not old and not soft. Okay, we have a lot of new mathematics to discover for this data, machine learning from data problem that has been around since the ancient times. Okay, so with that said, I come to the end of my presentation. I'll be happy to answer any questions.
Thank you, Professor Lee. Now we are open for questions from the floor. Any questions? If not, maybe I'll just start with a question. So for someone who is interested in machine learning, do you suggest for someone who wants to do a PhD and is interested in doing machine learning, do you suggest for them to go join a math department or computer science department or IDS?
Well, it depends on really on where your interest lies, right? So I would say that all of these departments do, certain aspects of this machine learning from one way or another. If you're mostly interested in the practical aspect, then it's always good to join, and work with a faculty that works on practical problems. And then if you're interested in the mathematical basis of if the mathematics is what you're interested in, then you should definitely consider joining, going with the supervisor in the mathematics department. But with that said, many of us, as far as I know, work on interdisciplinary areas. So, like, for example, I'm most interested in mathematics, but I also work with many colleagues across different departments on practical problems of this type. So. Yeah, so I would say that all of this, works really well for anyone who's interested in certain aspects of machine learning. For example, some of my students, actually many of them are from different departments, not just from mathematics, and also co-supervised across with colleagues in engineering and in the other sciences.
Great. There's a question by Shukai. Are there any machine learning projects being done in the field of finance currently?
Yes. So this is a very current, very interesting area. So maybe to give one example, as I said, in this talk, one of the main challenges that the modern machine learning is trying to resolve is the problem of high dimensions. That means when you have many different inputs interacting together, traditional methods fail. This is especially the case for finance. If you think about the portfolio selection problems, like you're trying to invest, into some stocks, and there's 300 of them. Okay, what's the best way to do it that balance, the risk and the reward for every single stock? This you can formulate as a mathematical problem. Right? This is a very precise mathematical problem you can formulate, but the problem is you cannot solve it because it's in maybe 300 dimensions. Okay, but modern machine learning offers a way to resolve this problem by actually solving this problem approximately in 300 dimensions. Now, this is a very exciting area, has open up, a lot of new applications. So if you are interested, the keyword is, solving partial differential equations in high dimensions using machine learning, which is, useful in, say, Hamilton-Jacobi equations that arise in finance.
Okay, yeah. I think the part-time PhD can be answered in the booth. So the other question is, while I have done a major in math, how easy it is for someone to do a PhD in this area? Secondly, how easy is it for someone who is interested in interdisciplinary focus on business and operations research and data science? All of them require math. So
yeah, so I would say that the mathematics that underlies machine learning is not one particular area, right? So if you hear the previous talk as well, I mean, there's a lot in optimization theory, operations research. So I would say that it is extremely broad, and it's not possible for anyone to know all the math. Okay, so that's not the problem. But I think so what is the, let me see if I can see the question precisely.
Yeah, the question is by Rajesh. This question that it says answered live. Yeah.
Okay, so I'm trying to see if I can.
Okay, so
okay, yeah, I'll click on the Q&A, right?
Right, click on the Q&A.
How come I cannot see it? Okay, now I see it. Yeah, okay. Right. Yeah, so I think, if for interdisciplinary kind of candidate, you really want to focus on a problem, right? That has both components of applications and mathematics, and then very often people do find a joint, advisors from different theory and also applications to work on this problem. So I would say that that's very often the case. So the
Okay.
mathematics you can pick up, in courses, around the university.
Okay, there's one question which is upvoted. How do you know math is the career you want to pursue? What are the challenges and enjoyment? Do you still enjoy math?
Yeah, certainly. I mean, there's my primary interest is in mathematics, because I think how do you know you like math is that you are willing to work on seemingly pointless problems. Okay, but it's actually not pointless. So the idea is that if you enjoy abstracting certain practical problems into a very precise language, solving them and asking what kind of insights do we have for the practical problem, then this is a very good area to work in. This is especially true for applied mathematics in machine learning, because very often the insights you get from mathematics can directly translate to applications, because they are so close, right? The machine learning problems formulated in mathematical problems, you don't lose much. But as in other areas, you have to make a lot of idealizations and assumptions that prevents you from sometimes directly applying. But for machine learning, I think this is the advantage.
Okay. There's one question which is also one that I've always wanted to know the answer to. How do you deal with high dimensional, but small sample size in machine learning? In a lot of biological things, is usually high dimension, but small sample size.
That's a great question. So actually, even in modern machine learning, like if you think about image recognition, right? We can do very accurate recognition of images that are, let's say, 5112 by 5112. So that image dimension is extremely high, right? But the number of samples is way less than what you need. And also, like, the dimension of my model, like the number of tunable parameters is extremely large. So what happens is that we discovered, if you train or learn the model using certain algorithms, okay, like stochastic gradient descent. Okay, I wouldn't say what that is, but if you use certain algorithms and you apply it the right way, it has a regularization effect that allows you to still train a good model on very limited data. So this is something that mathematically we still don't have a correct, a complete understanding of. But this is a fact that we have discovered from this modern machine learning, deep learning, is really that we are always working in the regime where the number of data is way fewer than the number of tunable parameters that we have in our models.
Okay, so I think maybe you can do one more question. Which one would you like to answer? The first or second with 2 upvotes?
Second with 2 upvotes. Okay, so is there any?
I think the second one can be answered in the booth. So maybe the first one.
Okay,
Is
so
there any project about the interpretation of the ability of deep learning models? How do you think that mathematical theory advancement will affect the industry of deep learning?
Yeah, so that's a good question. So there's a lot of work. Actually, one of the most important questions is the interpretability, right? So why does it work? And when it makes a certain prediction, why does it make a certain prediction? Now, to understand this will be of fundamental importance to applications. For example, very often when you try to market some sort of deep learning solution to an industry, let's say in medicine or something, and when you make a certain prediction, very often people ask, so how do you arrive at this prediction, and how safe is this prediction? What is what are you sure about this prediction? Okay, so to understand this is very important, because then it expands the realm of applications of a lot of these machine learning models. So I think it will affect the industry in a fundamental way. But of course, it's a very difficult problem, because the models are very complex and the algorithms are very complex.
Okay, thank you very much, Professor Lee. It now gives me great pleasure